Hi, so today we've got another interesting piece of formerly expensive lab equipment. This is a Caliper Labchip XT, which is a piece of equipment used as part of the process of DNA sequencing. I can't remember what I paid for it, but it wasn't a great deal. And basically this is used to perform a process called gel electrophoresis. This is quite a common process for sort of chemical and biochemical applications, where an electric field is used to separate molecules of different sizes by applying electric field over the molecules in a gel. And this actually uses gel in like a chip form. There's like a cartridge that fits in here that has chemicals and electrodes built in, as well as some optical windows. So the idea is this can perform the electrophoresis process, and it uses a laser to excite fluorescent dyes so it can monitor the process. The idea is this will break up DNA strands into specific lengths for further analysis, and you can specify the lengths, and so this will sort of apply the appropriate voltages and monitor the progress, so you end up then with the bits of DNA you want that you then go on to stick in your DNA analyzer. The fact that this was sort of cheap on eBay suggests, I'm assuming this is probably an obsolete process that's probably been superseded by newer, faster, cheaper processes. Unlike the previous analyzer, I found the consumables don't seem to be quite so ridiculous. I saw one, and this is the photodiode. Can't see any obvious part number markings. There's a number on the bottom which looks like a serial number, and I even had an image search and I can't find anything even in the same package, so it's clearly something vaguely exotic. It might be something that's optimised for specific wavelengths, and it's obviously quite a large area, so it's probably quite an expensive part. Come in it, and then others you add, like the dyes and so on, I think you add later, and then you use a pipette to take out the samples afterwards. So you can't really see a great deal from the top. There's these the optical windows for the optical analysis. There's a barcode reader, so there's a barcode to uniquely identify each chip, and there may be some calibration and batch information on that barcode as well. And in the top there's a load of electrodes. These are sort of spring probe type electrodes that sort of make contact with the chip when the lid's closed down. And nothing much at the back, just USB host, USB device, power in, and that's pretty much it. This is the first cover that obviously comes off. Nothing to see really here. There's a flex cable that goes up to the hinged lid. There's a micro switch, which is probably in it because these contacts can have sort of high voltage on it. That's probably, yeah, she says interlock, so that'll be the interlock function. It says Quetzal interlock USB. I don't know what Quetzal is. Maybe that's the internal product name. In fact, that connector says HV Pogo, so there's sort of Pogo pin type high voltage connectors. And interesting, there are sort of 3 buttons on here, which, yeah, they're not normally user accessible, so I presume these are for some sort of test functionality. And so in the lid we've got these spring-loaded pins that make contact down into the cartridge. There's also a little mirror here, and that's going to be for the barcode reader, so that's obviously reading the code from the side of the chip by this mirror. And this whole top assembly comes off this top. This is a sort of big, about 8mm thick solid piece of aluminium. So you'd expect nice sort of chunky construction in a sort of 24 grams worth of kit. Some nice sort of braided sleeving, sort of fully labelled cable assemblies, all in this braided sleeving stuff. So you see on the back of this, so there's the barcode reader here. There's an assembly here which I think is probably lasers with fibre optics going out and going into the block here. There's presumably some sort of optical detector somewhere. That might actually be, there's another fibre here, and that's going down into this block on the main PCB, so I imagine that's probably the optical detector. It's not big enough for it to be a photomultiplier. I don't know what, it may just be a photodiode, or we've got a separate cable assembly. I think this is probably going to be the high voltage. This has got this, like, feels like silicone. So this is just additional insulation coming from over here, and there's a whole load of I'm guessing MOSFETs plus read relays, and this whole area of the PCB is conformal coated, so this is clearly the high voltage. In fact, there's a label on there that says -HV in, so there's probably a high voltage power supply underneath there that's supplying this section. Take a look at that. Might be quite interesting to see how they deal with the high voltage. Electrophoresis generally works in the sort of few hundred volts sort of range, and in fact if you want a high voltage power supply cheap, it's worth looking at electrophoresis power supplies, because they're generally available quite cheap as surplus. You typically give out anything up to 1000 volts at tens to hundreds of milliamps, so they can be quite nice high voltage power supplies, and obviously quite dangerous, which is always fun. So this whole thing's this is also enclosed in like a folded aluminium assembly, so I think if we just take everything out we should be able to get a better view of what's going on. This whole board assembly comes out, it's on a sort of aluminium sort of deck. A high voltage power supply. This is a 15 watt 0 to 600 volt negative output power supply. Doesn't do much when you power it up, you just get this sort of cycling pattern on this 14 segment display. I did actually find the software and installed it, but the problem is it needs a USB dongle, so I couldn't get it to do anything interesting. So let's take a look at these boards. This is the enclosure that the fibre optic from the optical ports goes into, and see there's just a there's a lens and a filter. I'm sure that filter is going to be to filter out the laser green wavelength, so that it only sees the fluorescence wavelength from the dyes. Under here we've got this sensor. Now I'm pretty sure this is a large area photodiode. Sometimes for high sensitivity things they use I think called an avalanche photodiode, but that uses high voltages at 100 or 200 volts, so if that was the case I'd expect to see some sort of high voltage filtering cap, which I'm not. There's quite a lot of signal conditioning underneath here. These are some ultra low noise FET packages, and then there's some various op amps and some AC converters there. And this is the photodiode. Can't see any obvious part number markings. There's a number on the bottom which looks like a serial number. I did a bit of hunting around and I came across this. I think it may be this one, which I found on DigiKey, which is a UV enhanced photodiode. Which, although this one looks like it's aimed at UV, it could be just a similar device, or just the fact it's got extended UV. It may also be more sensitive to the shorter wavelengths and the visible. I don't quite know exactly what wavelengths of fluorescence this is designed to detect, but this is $283 for a 5-off, so obviously quite an exotic device. Looking at the rest of this board, so we've got this high voltage area up here. This has got conformal coating, probably mostly to avoid leakage and also any effects on condensation or moisture. Obviously you've got a high voltage on there. Even a tiny amount of moisture could cause some leakage currents. There's it looks like there's four channels, and there's a read relay on the output of each channel. I don't know if that's for enabling, that may be for a safety interlock. That interlock circuit on the top looks like it interlocks it certainly interlocks the lasers, and it may well also control these read relays. Well, I'm surprised they didn't. If these are just for interlocking, I thought it might be easy just to switch the power to the high voltage power supply, but maybe there's other reasons for these switches being here. And there's two 500 volt P-channel MOSFETs on the output, various analog op amp stuff, and these are driven by a D to A converter. There's probably some current sensing feedback on here, I'd imagine, as well. Down here there's 4 drivers for the laser diode, so you've got some 5 ohm current sensing resistors, and these MOSFETs, these will be setting the laser diode current, and there's probably going to be some photo sensing, some optical feedback coming back from the lasers, so these will be adjusting the laser current to get consistent output. There's another relay down here. I wonder if maybe that's to do with interlocking the laser side of things. This board is clearly either adapted from another product or designed for use in multiple products, because there's a few. For example, here there's a connector there that says HVPS, but the high voltage power supply is actually plugged into this over here that's marked light, and there's a connector here marked fan power, and that was actually connected up to the top board for the laser power supply. So there's also a few markings on the other board that are obviously for a different piece of equipment. Not much else on here, so some small D to A converters here, driving the laser drivers, power supply stuff here. There's probably some maybe some power supply monitoring. There's a isolated DC-DC here, but the output positive is connected to ground, so that's just generating a negative supply for all the analog stuff. This whole unit runs off a single 24 volt supply, so obviously that's been converted to the various low voltage supplies by all this stuff here. And on the back there's just a Spartan 3S50AN FPGA. It's a fairly small FPGA with onboard non-volatile configuration memory. On the back of the high voltage area, there's a few chains of resistors for dividers, presumably for voltage sensing, and just a few other passives. That's the back of the optical amplifier that we saw before. And there we've got this name Quetzals. That's clearly some sort of project name. 2011 test date on there. Digital board. Now here we see evidence that, again, that it's for some other products. We've got connectors marked encoder, limits, motors. So this is clearly for some sort of bit of equipment that's got, yeah, probably stepper motors and limit switches, maybe some sort of sampling thing that sort of dips into different compartments of a gel plate or something. DACs, solenoids, SPI interface. This one's unused. Couldn't figure out exactly what these chips are. They might just be protection, or they could be sort of drivers or something. One thing that was slightly puzzling, some quite obscure chips here. These are LS7166, which are 24-bit programmable counter chips. I can only guess that these are maybe for dealing with rotary encoders, but if they've got the FPGA on there as well, it seems a little bit, I don't really understand why they would need those, but it's a fairly obscure chip. Also, here we've got Cypress USB interface, so that's obviously the main USB interface for the processor. The main processor is Texas Instruments TMS320F2812 DSP. This has got onboard flash, some external RAM here, another 3S50AN FPGA. There's another connector here marked panel I/O, so again that's clearly for some sort of instrument that's got some front panel, maybe keypad and LEDs or something. Again, there's a whole load of these chips, so the fact they've got the same chips all the way around here makes me think these are maybe sort of static protection or something rather than drivers, or they could be LED drivers or something. Got this 14 segment display, which is probably for error codes. Maybe it shows a single letter or digit error code, or maybe even scrolls around some sort of meaningful error message, but say all it does is on power up is you get that circling pattern. There's a few RS-232 ports. Again, none of these are actually used in this instrument. There's one here on the DSP, another two here. This is actually a USB hub, so that the PC interface plugs into here, goes into this hub, and then from there we've got these two FTDI USB to serials, which are running the serial port. So again, that's probably for a bigger instrument that's got some internal RS-232 peripherals. There's also an RS-485 connector here again, which is probably for another version of another bit of gear that's got some internal RS-485 kit. And there's also two connectors. Here there's one rear panel type A, and there's also this cable here which went to the barcode reader. So obviously for something like this, because it's always going to be attached to a PC, there's no point in, for example, interfacing the barcode readers to this stuff, because everything can just go to the PC. So that just appears as a USB device to the PC, and the PC deals with the barcode peripheral, and it can also access these serial ports. Again, if we've got some sort of serial device internally, the PC just talks directly to that. There's no real need for the DSP to deal with that. All this has got to do is just deal with all the analog and digital stuff going on with the actual cell. And considering how little this is really doing, it's basically just applying high voltages and turning lasers on and making measurements. That DSP is probably overkill for this product, but so this is probably a board that was either designed for this and other products, or just a board for another product they've adapted. There's sort of one bodge wire on there, another one on the back, but there's nothing much here. There's, the rest of this just some passives and stuff. And this is the high voltage power supply from Matsusada, made in Japan, where all the best stuff comes from, of course. And this is all potted inside. This is sort of overkill for a 600 volt power supply, but this range of supplies goes up to 30 kV, and obviously that sort of level you would need potting to avoid breakdown and sort of flash over and so on. This is designed as this is spec'd as a very low noise supply, so it's designed for sensitive applications, sort of photomultipliers, ion sort of physics, that sort of thing, sort of specialist applications. And the input is just a 24 volt supply and a control voltage input to set the output voltage, and there's also a reference, so you can just connect a pot across here to set the voltage, and there's a current monitoring input. This is up to 600 volts at up to 25 milliamps. Okay, so this is the business end at the top. This is the barcode reader module. It's two parts. There's a camera and illuminator module there, and then this, which is the decoder So this takes this. I think it's just a this is an image sensor, so this is just taking that image in and doing all decoding. This is an off-the-shelf product, so this handles sort of 1D and 2D barcodes and all sorts of other things. It looks like it's a package on package. This chip on the top is a micron flash chip, so it looks like this is on top of another. It's probably one of the various system on chip devices, yeah, with a an image interface and a reasonable amount of processing to decode the barcode. And this is the block with the 4 laser modules in it. So you see these sort of cylindrical modules in there, and these couple into fibre optics. So these fibres go into the optical block, and then 4 fibres come out for sensing. These merge into a single fibre into this, which then when it's that goes into that sensor module. So I sort of shine some light into the end of these. You can see the light coming out the other end. Okay, this is the board that was in the top. Not a huge amount on here. We've got the connector for the barcode scanner. All these buttons seem to be connected just to that scanner connector. There's obviously some hardware sort of button functions on this connector. I'll see if I can find the information on this module later. DNLD, which I'm guessing is maybe some option to allow firmware downloading. 3.3 volt regulator there, producing the supply for the barcode reader. There's a micro switch there, which is for the interlock, which appears, I think that's connected through this relay. I thought I heard this relay clicking when I was opening it. What's slightly surprising is there doesn't appear to be a direct hardware interlock for the high voltage supply. The high voltage comes into this connector and goes straight out sort of through the ribbon cable to the pogo pins that go onto the top. I'm a bit surprised there wasn't a something which interrupted the supply into the high voltage converter. I'm sure there'll be some sort of protection in this circuitry here. Perhaps they're using these read relays to do that switching. But on something like this, you'd expect, if you've got 600 volts on there, you'd certainly want to have some non-software dependent way of it shutting that off when you open the lid. This is the cable that transmits the USB signal from the scanner. But they've done a bit of a bodge here. They sort of covered it in this is covered in glue, and it looks like they've taken off one of these USB-A connectors and just soldered this directly to get the internal connection to the barcode scanner. So this is a this barcode decoder. It's a symbol PL4507. Tons of information online. There's over 400 page manual on this. It does USB, RS232, configurable up the wazoo. You can do pretty much all sorts. It also reads standard barcodes, and it also reads QR codes. And it doesn't really care too much about orientation. It's obviously it uses a Marvell SoC there, so it's obviously got a lot of processing power. Sort of grab the image and just try reading pretty much any sort of barcode from that image data. And there's also a full sort of set of drivers and an API and a software development kit online for this, so you can just play with it. You can get barcode data out of it, and you can also actually get image data out of it as well. So it's quite a neat little module, and I've hooked it up now. This is just powered and run directly from USB, so I'll literally just take USB straight onto this board, just using it to break out the edge connector, so it's not connected to anything else. So this barcode reader comes in 2 modules. There's the actual reading head. Obviously they've done it this way for maximum flexibility for packaging for different applications. So there's a decoder module, which has got as a Marvell SoC, a flash and RAM chip and various interface chips. So that's doing the actual processing, and this is basically a camera module. There's sort of 2 red LED illuminators with lenses on them. But one thing I noticed when I was looking at this, there's also a laser diode inside there. And looking through, this is a CSI interface camera, and looking through the documentation, there's actually a facility for a laser aiming pattern. And actually looking at the front, there's a plastic sort of grill or lens assembly, but they've put some black ink over the top of it, so maybe we can actually get that working by reconfiguring it. So yeah, if we just peel that off, you can see there's just a sort of grid, so I'm guessing that just projects a grid to show where its field of view is. So we can get that working. Okay, as with most barcode readers, you can actually configure them using barcodes. So this is the normal press to read mode. But I can then just go auto aim. It gives me this nice laser aiming thing. Okay, auto aim. It's got a motion sensor in it as well, I think. So if I scan auto aim, yeah, I think it's got rather sensitive. See, it's almost not turning off, but yeah, so it's got this. As you can maybe able to see, as you sort of pull further out, you can see this pattern turning into dots. So they're using some sort of diffraction grating or something to generate that cross pattern. It's quite cool. Things are always better with lasers on them. So speaking of lasers, the only thing better than a laser is 4 lasers. These seem to be sort of modules that are screwed into this block. This whole block was actually insulated from the panel that it was held in with nylon screws. So I suspect maybe the case is non-isolated on these, which is not uncommon with lasers. And these are the fibre optics, so these just come into this block that's clamped down, which has got the polished end of the fibre there, and a small focusing lens in the block. Now I'm assuming these are going to be DPSS screens. I think it said, I saw 532 nanometers somewhere. Body with a lens there. Actually looking at the side of this, I think this thing on the side is a feedback photodiode. Okay, maybe slightly tricky to see, but this is the actual, you see the end there of the actual laser assembly here, and then there'll be the infrared pump diode back here, sort of firing the infrared into this assembly where it lasers at 1064 nanometers and then gets frequency doubled to the green 532 nanometer output. Problem is obviously the laser like this, you've got no idea what its design current is, but we do have more than one of them, so if we smoke one at least that means we know what current not to go over. Okay, I've just connected this to the power supply via a 22 ohm resistor. Even if you've got a constant current power supply, it's not a good idea to use that for powering laser diodes because you can get spikes when it turns on and off. I'm just sort of slowly increasing the voltage. I'm also monitoring it with a monochrome camera because that'll see any infrared illumination happening. I'm already seeing that, although you probably can't quite see it on this camera because it's got an infrared filter. Yeah, you can just about see the emission, but obviously you need to be careful because these things put out a lot more infrared than they do visible. But in this configuration there will be some coming out the side, but it won't be like a beam coming out the side, so as long as you're at a reasonable distance that's going to diffuse, so it's not going to be too hazardous. So I'm just going to start increasing the current to see if we get any green. About 85 milliamps at the moment. Lasers tend to go sort of increase. They've got this thing called threshold current where they hit a certain current before they actually start lasing, and then the output increases quite significantly. Okay, so we've now got some green going on. That's at 90 milliamps, so we've got very dim green output there. These lenses are probably designed to focus quite close because they were designed to be coupling into the fibre. The output's now increasing, it's up to 100 milliamps. It's now getting quite nice and bright, so it's about 100 and 120, but say without knowing what the output of these is supposed to be, it's a bit hard to know how far to go. Let's put the lens back on so now we get quite a nice small beam. This is the assembly that the fibres go into. They just seem to have just sort of glued a pair of fibres and polished the ends. I think optical alignment is probably not super important on this because I think there's a you get like a calibration cell that you use so that should deal with any unevenness. So as long as everything's nice and stable, they can then calibrate the actual optical characteristics using that. And it looks like the way they align these is they just got these. The fibre comes into this block, and then there's a couple of clamping grub screws. So this thing all gets clamped together, and by slackening off these grub screws you can sort of move this around to optimise the light and then clamp it back down again to nail down the position. And when this is all aligned you get quite a bright light going into this section. And then if you look at the end that goes in the detector, if we sort of create some reflection, You can obviously see that coming back for the sensor, and obviously that then goes through that lens and filter, which cuts all the green out. And this is the filter that was in the that detector assembly, and you see that just completely blocks. See, it's sort of fairly transparent at other wavelengths, but it totally blocks the output from that green laser. It's nothing. I can't even see anything with my eye, let alone the camera's obviously not super sensitive, but even by eye I just can't see any green at all through that filter. So it's obviously a very narrow band, but very high attenuation filter. If you actually look at it with the laser direct, obviously don't do it with your eye, just do it in front of the camera. See, that's super bright, but with the filter we just see absolutely nothing. And to sort of illustrate the principle of the fluorescent, this is a bit of fluorescent acrylic, which sort of fluoresces quite nicely. So here we can see that perfectly well through the filter, but we just don't see any of the green at all, so we can tell how much of that fluorescent material is there. Now we've got that filter in to filter out the light that we're shining at it. So a few interesting odds and ends, nothing sort of hugely fascinating, sort of few lasers, fancy photodiode. I looked up, I only paid 50 quid for this, so it's probably just about worth it, but I think the original $24,000 price tag was possibly slightly piss-taking considering how little is actually in this, but I'm sure they spend a lot on the R&D and all the other stuff.